Have you ever just stopped and thought about your phone? I mean, really thought about it? This little slab of glass and metal is doing a million things at once. It's streaming video, it's navigating your car, it's talking to your earbuds, all at the same time with zero wires. It feels like magic, right? Well, let's dive in because it's not magic. It's something way, way cooler. It's an absolute marvel of microscopic engineering. So seriously, how does it do that? How does one little device speak all these invisible languages, 5G, Wi-Fi, Bluetooth, GPS, without just turning into a garbled mess of signals? The secret isn't out there in the cloud. Nope. It's etched onto tiny little chips, in a world so small it's measured in micrometers. To really get this, we've got to shrink ourselves down and look inside at the hardware that's built specifically to handle these radio waves. We're about to peer into the world of microwave integrated circuits. Okay, so what is a microwave integrated circuit, or MIC for short? Think of it like a tiny specialized city built for one thing and one thing only, managing super high-frequency signals. This isn't just a component, it's the very foundation that makes all of our wireless tech, from a phone call to 5G streaming, actually work. Now, you're looking at a really crucial evolution here. In the early days, you had hybrid MICs. You can think of those like building a city with prefab houses. You make all the parts separately, and then you wire them all together on a board. But the real game changer, the thing that makes your phone possible, is the monolithic MIC, or MMIC. This is like carving an entire intricate city out of a single block of stone. Every single component is formed right onto one tiny chip. That leap right there, that's why the powerful devices we use every day can fit in the palm of your hand. And of course, every city needs roads, right? Well, inside these microscopic cities, signals don't just float around randomly. They travel on these incredibly precise, carefully designed pathways. We call them planar transmission lines, and they are quite literally printed highways for radio waves. And just like a real city has 8-lane freeways, busy avenues, and quiet little side streets, these circuits have different kinds of highways for different jobs. Engineers have a whole menu of options to choose from, things like a microstrip line or a coplanar waveguide. Each one is designed for a specific purpose to guide a specific kind of signal in the most efficient way possible. So, why choose one highway over another? Well, this gives you a little peek into an engineer's decision-making. You can see some designs, like the microstrip, can handle insanely high frequencies. We're talking up to 110 gigahertz, and they're super small. Others might be a bit bigger but have other useful properties. It's always this complex balancing act between speed, size, and signal integrity. It's all about picking the right road for the right traffic. Okay, so we know what these highways are. But this brings up a much, much bigger question. How in the world do you design something like this? You're building microscopic structures to perfectly control invisible forces that move at the speed of light. I mean, the challenge is just immense, right? You can't just sketch it out and hope for the best. You can't eyeball it. The scales are too small, the physics are too complex, and you're dealing with forces you can't even see. So how do you build these perfect little highways for invisible waves without it being a complete shot in the dark? You do it with math, but not just any math. You go to the source. You use the fundamental rulebook for how electricity and magnetism work in our universe. As the source material for this explainer puts it so perfectly, perhaps the most important equations are Maxwell's equations. This is the bedrock. This is the foundation of everything. And here they are. Don't worry, there's not going to be a quiz. You don't have to solve them, but you just have to appreciate what they are. These 4 elegant equations describe everything, and I mean everything, about how electric and magnetic fields behave. For a radio frequency engineer, these aren't just formulas. They're like the 4 commandments of physics. You simply cannot break them. But you know, knowing the rules of the universe is one thing. Applying them to design a super complex microscopic highway system is a whole other beast. Trying to solve these equations directly for a real-world shape is often next to impossible. So engineers have a secret weapon, a kind of mathematical alchemy that lets them solve these impossible problems. And that secret weapon is called conformal mapping. And trust me, this is one of the most clever, elegant tricks in all of engineering. What it lets you do, essentially, is take a shape that is a complete nightmare to analyze mathematically and morph it into a really, really simple shape where the math is suddenly easy. So here's how the magic trick works. First, you start with your challenging real-world shape. Then you apply this special mathematical function, the map, that basically redraws it into something super simple, like a basic capacitor that you learn about in Physics 101. In that simple world, the calculations are a breeze. And here's the brilliant part. Once you have the answer in the simple world, you just use the map in reverse to bring that perfect solution back to your original complex shape. It's an absolutely beautiful way to get precise answers for impossible-looking problems. Okay, so let's zoom all the way back out. We've gone from the fundamental laws of physics to some really elegant mathematics, and now we're back to that device that you're probably holding in your hand. 110 gigahertz. Just let that number sink in for a second. That's a frequency that some of these tiny little highways are designed to handle. So what does 110 gigahertz actually mean? It means 110 billion electromagnetic waves are being perfectly corralled and guided down these microscopic paths every single second. The level of precision needed to make that work is just staggering to think about. So what should you take away from all this? First, your phone isn't just a gadget. It's a whole universe of perfectly engineered microscopic highways. Second, those highways, the planar transmission lines, are the unsung heroes guiding all the invisible signals that connect you to everything. And third, and maybe most importantly, this is all possible because of powerful, beautiful mathematics. It really isn't magic. It's a true marvel of precision engineering. So the next time you tap your screen, send a message, or just connect to Wi-Fi, maybe you'll think about it a little differently. Will you think about those 110 billion waves a second, all racing down those invisible highways, built on a tiny speck of silicon right there in your hand?